Here we are to talk about limits and continuity in Calc 3. So, yes, there's a little bit of math jargon here at the top just to say, hey, for a limit to exist, the curve has to be predictable. I have to be able to expect what that value is and not have some kind of jump discontinuity, infinite discontinuity, undefined impossible value is all this is saying. This is saying, hey, when I get reasonably close to anywhere, I should be within a reasonable distance of an output. Okay? When I'm in a neighborhood that's fairly close to this coordinate, my distance from the output should be fairly close, within a distance formulas away. Now, I put that up there to give you the official definition because we've never officially defined what a limit is. The unfortunate thing is when we're in Calc 3, I can't just do left-hand limit equals right-hand limit, right? Because when we're in Calc 1 and 2, we just have 2D. And there's only one way to come to this point. If I want to get to this point, I come from the left or I come from the right. Anywhere else is not part of my function. But out here in Calc 3, we have functions that are more complicated, that have 3D space, that have lots of options. Like if I pulled up a picture of a mountain, and I wanted you to climb to this top of the mountain right here, I mean, there are so many different paths we can take. Come on, where's my mouse? There it is. There are so many different paths we could take. I could be coming up straight up this face if I was a super mountain climber. Maybe I come from over here and I go through over here and get to that mountaintop. I come from over here and I get to here. But what this is to show you is that I cannot simply say left-hand limit equals right-hand limit, therefore the limit exists. Is not an option, because how many paths do I have to the top of a mountain? Mathematically, I have infinite paths to get there. But the point is, I have to pass through the coordinate in question. So, as we do this, we just have to make sure that we pass through the coordinate in question. Any path I take has to go through the coordinate in question. In this case, the easiest way to evaluate a limit is direct substitution. So I do that. I directly substitute. I've got 1 squared times 2 cubed minus 1 cubed times 2 squared plus 3 times 1 plus 2 times 2 is 11. I trust you to do the calculation. If I could plug it in and have no issues, I should plug it in and I should have no issues. It's when we have those kind of rational functions, those jump discontinuities, the piecewise we won't touch as much, but those infinite vertical asymptote feeling types of equations like these do take a little bit of finesse. And honestly, rather than spending our time proving that something is continuous, we're going to prove more often that things are not continuous. So all this says is, if I head towards that limit as I follow path 1, if my function heads towards this limit as I go to the same coordinate, and that limit is different, along C2, a different path, then the limit does not exist. If I come up the face of the mountain or I come from the left side, I should approach the same place. If I approach a different height, if I approach a different output, then there's a disagreement. The quote-unquote left-hand side doesn't agree with the quote-unquote right-hand side, and therefore it is not continuous. But this does take a little bit of finesse, to take strategy, and we have to figure out what this word path really means. All right. The first thing that I always try is that I'll always try the path where x equals 0. Super simple. Path x equals 0. I guarantee that the path x equals 0 goes through this coordinate. Apologize. I'm following this path, so when x is 0, that means my path, if I correct my notation, would be 0, y. Because along the x-axis, all I would have are y values, where x is constantly at 0. Actually, this is following the y-axis when x is 0. My bad. So then my limit up here, well, x is 0. I get negative y squared over y squared. That equals negative 1. Let's try a new path. How about I try the x-axis, which is where y equals 0. Well, when y equals 0, my lim x0 approaches 0, 0. My bad. I should have put approaches 0, 0. A little bit of bad notation over there. But this becomes x squared over 2x squared, and I would just get 1/2. And because the quote-unquote this limit is not equal to that limit, I really don't want to say left and right-hand side, but that's the idea. That left-ish side doesn't agree with that right-ish side. The up-down direction does not agree with the left-right direction. The left-right direction doesn't agree with the up-down direction, however you want to say it. But yeah, you'd say because negative 1 is not equal to 1/2, lim D and E. Let's keep going. I'm going to choose path 1, which is just going to be x equals 0 again. Right? I'm choosing these paths because I immediately recognize, hey, as this approaches 0 over 0, like I know I get a little L'Hopital's, but we're not quite taking derivatives for this guy. It is a limit. So it just gets messy, right? But what I'm going to do here is I'm going to use those paths. X equals 0 along the y-axis, y equals 0 along the x-axis, and see if I can get a disagreement to prove the limit does not exist. Because I know I get a 0 over 0 weird case here. Sorry, when x equals 0, limit 0, y approaches 0, 0. The path 0, x equals 0 definitely goes through my coordinates, so I'm allowed to use it. And now all of a sudden I get 0 over y squared is 0. My second path, we take that y equals 0, lim x comma 0 approaches 0 comma 0 of this function, which now becomes 0 over x squared. Also equals 0. So somehow my two easiest paths don't work. Somehow my two easiest paths produce the same limit. So when I come from the left, it's the same as the right, is the same from the top, is the same from the bottom. So now I have to find a new angle to come in at. And so if I want this thing to reduce, I want to choose something that's going to make the degrees match. For example, what if I made x equal to y? Does the path y equals x go through the origin 0, 0? Yes. So this is a valid path to take. Well, if x equals y, that means all the y's I'm going to replace with an x. So this becomes x times x over x squared plus x squared. What is that? X squared over 2x squared. I got 1/2. A disagreement. Thus, 0 does not equal 1/2. Lim D and E, right? A little bit messy on some of my notation things here, and I'll apologize for that, right? I shouldn't be writing limit if I've already substituted the value in. Fair. But for the sake of space and for the sake of understanding, I think you know exactly what's happening here. So my rules for strategy number 2 is that I need to find a workable continuous curve that goes through that point. AB has to be on my path. I want to substitute so my denominator, or even the total degrees, are equal, but specifically the denominator, so they kind of group up together. I always want to use an axis as one of my paths. So I head to the back. Look, another limit. I'm looking at this thing. Let's try my first path. X equals 0. Well, I know that when I plug in x equals 0, my limit 0y approaches 0, 0 of this function, where x equals 0 turns my numerator into 0 times 1 is 0. My denominator into y to the 6th, so I get 0. I just take a cursory glance and go, hey, what if I plugged in y equals 0? The whole numerator is multiplying. I'm going to get 0 again. So I need a new path that is going to make my degrees match. What is going to turn a square into a 6th power? Hopefully you say cubit. What if I took the path x equals y cubed? Before I go any further, let me make sure, does this path go through the point 0, 0? I guess that's not written up here. Limit x, y approaches 0, 0. It definitely goes through the coordinate 0, 0. So let's make this fix. Let's do this substitution. Now my limit is going to be y cubed comma y approaches 0, 0, which it does. When I replace this y cubed, this becomes y cubed times y cubed times cosine of y cubed. That's a lot of cube. This becomes 2y to the 6th plus y to the 6th. So now I'm going to get y to the 6th cosine y cubed over 3y to the 6th. When I reduce that fraction, I get a nice 1/3 times cosine y cubed, and as that approaches 0, I would get 1/3. Finally, the disagreement I was looking for. As 0 is not equal to 1/3, the limit does not exist. Period. I do want to show you what one of these pictures looks like, just so you understand, hey, these are the type of functions we're talking about. Right, from the get-go, I kind of see this wavy plane. Right, you can see the undulating surface kind of coming and going. You see a little bit of a cosine wave when I hold it this way. You can see a little bit of a, I don't know exactly what, like a twisted cubic when I hold it that way. Right, but you can actually see this thing is starting to break. As I get closer and closer to 0, 0, this thing is freaking out, and it does not know what to do, especially on the YZ panel. So, that's telling me I'm very likely to have a DNE. It's not very likely that these jagged, random paths are going to head to the correct coordinate. And so if I follow, you can almost see it here. Do you see the cube coming through? And it's not even that one. Hold on, let me flatten it out. You can almost see that x equals y cubed coming through here and going out. And this path, we can't see height. I flattened it to avoid height. But what you do see is that that path goes through 0, 0. And the math tells me, hey, guess what, man? The math tells me that it goes to 1/3 instead of going to 0. Okay, enough of this. Let's knock out some more examples and get out of here, folks. I'm on this one. This is not nice, because when I plug in 0, I'm going to get 0. When I plug in 0 for y, I'm going to get 0. I'm trying to think of another path that's going to make my whatchamacallits match. But wait, did you notice something? Prove it does not exist. Prove it does it exist? This example's different. This example says find the limit. That's telling me the limit does exist just by the instruction. So is it my job to show that a million paths converge? Am I going to show infinite paths that all converge to the same value? No. What I need to do is remove the doubt from the equation. I need to remove this denominator in such a way that this thing will reduce, no longer have a denominator, and have a very clear, always available answer. I see x squared plus y squared. What is x squared plus y squared? R squared. What is x equal? R cos theta. What is y equal? R sine theta. Hey, when xy goes to 0, 0, what does r go to? 0. And I will do a chilly polar substitution here. Numerator is yucky. R cos theta times R sine theta. Denominator, the square root of R squared. Because look, it's simplifying. R squared cos theta sine theta over R. R cos theta sine theta. Well, again, I should be writing lim everywhere. The limit as R approaches 0, well, it doesn't matter what the angle is. I don't really care what theta is, because when this approaches 0, this thing approaches 0. And it doesn't break. I've factored out that denominator to appropriately direct substitute and evaluate my limit. Very rare that we run into these, but whenever you see x squared plus y squared, you're jumping over to polar basically for this class. Now let's talk about continuous and domains, because that's going to make it clear whether this is going to be happening good or not, if it's a direct substitution or not. Like here, I'm thinking what domain? So this equation will always be okay as long as x comma y, right? Any real number will basically work, except this is x and y. This coordinate is in all real numbers such that x squared plus y squared does not equal 0. Duh. As long as x squared plus y squared doesn't equal 0, this thing's going to be just fine. So it'll exist everywhere that my denominator is not equal to 0. Seems kind of silly, right? This is saying, what's the issue with this one? Well, the issue with this one would be if a y is 0. So y is an element of all real numbers such that y is not equal to 0. Simple. Continuity is simple. How about this one? This should probably say f of x, y, z. Another little typo there, sorry. So I would have coordinate x, y, z in R3. This should probably be R2. Such that x squared plus y squared plus z squared does not equal 4. What's that shape? A sphere. So it exists in all of 3 space, is filled with values that blobby is filled with skittles that all have a 4th dimensional value, as long as it's not sitting in the sphere with a radius of 2. Down here, back to some just original continuity. You know how to do this. T is a real number such that it's not equal to 0, and square roots restricted to positive. Strictly greater than 0. All right, that was just a nice little continuity pause. When we're in 3 variables, we need a parametric path. That's just the truth. I need a path because I can't set a direct relationship from x equal to y. It's not exactly correct to set a path where x equals y equals to z kind of a relationship. We'd rather just use a parametric because I'm following a path in 3D space. A path in 3D space is going to be a space curve, and we love to represent them parametrically as we did the last 2 units. So, like it says, the first path, x0, y0 makes the z-axis. So, that x being 0, y being 0 makes the z-axis. The first path would be 0, 0, t. That's just along the z-axis. When I plug in 0, 0t, I get 0 for my numerator. My denominator, I get t squared, which gives me 0. Now on path number 2, this is where it gets interesting. It says path number 2, I still want to match the degree. So if I have a square and a square and a square here, what's going to give me squares in the numerator? If x and y have the same degree, if they're both t, that'd be t times t is t squared. T times t is t squared. T times t is t squared. So now my second path is just going to be t, t, t. Because when I plug that in, I would get and again, you want to make sure, hey, does this approach 0, 0, 0? It does. For the values of t that approach 0, my issue would be if this was like a t plus 1, I would have an issue. Again, if this path wasn't at 0, 0, 0, I might have to modify my path to not quite go directly through 0, 0, 0. It might be 0, 0, 2. It could be 1, 0, 0. You know, and I would be making adjustments here, maybe adding a cosine, maybe doing a t plus 1, maybe, all sorts of different opportunities there to change. But here we go. When I plug in t, I get t squared plus t squared plus t squared over t squared plus t squared plus t squared. That's just 1. And because 0 is not equal to 1, lim does not exist. Again, we spend the whole worksheet not exist, not exist, not exist. Very, very, very rarely do we have a limit that exists, and when we do, it's generally this clear and obvious. It's general, oh man, these are going to cancel and reduce. These are going to cancel and reduce, and so I'll get a clear answer. Or maybe I could have something like this, and I would be approaching the coordinate 1, 2. Well, when I approach 1, 2, there's no issue. I'm not going to be dividing by 0, so I'll just get a value out of it. Last problem. We're going to start with an axis to begin with. I do see y and y are individual and not multiplying, so I'm probably going to make my first path along the y-axis. 0, t, 0. All right, so when I plug in 0, t, 0, again, lim 0, t, 0 approaches 0, 0, 0, and it does, I would get 0 plus 2t squared over 0 plus 2t squared plus 0, where I'd get 1. On to the next one. I need another path, and I want to make these degrees match. I see I have a square and a fourth. What's going to turn a square to a fourth? If I square it again. So that means this x needs to get squared and squared to make a fourth. This y needs to get squared and squared to make a fourth. And this z needs nothing. So this path is going to be t squared. T squared. And plain t. Because that's going to get pulled up to a fourth degree, and that'll be a fourth degree. And then hopefully my numerator matches, and this all simplifies down. I double check, yes, this approaches 0, 0, 0, so I don't have much worry in that case. I'm just plugging and chugging. This thing becomes t squared times t squared plus 2 t squared squared. Squared squared plus t to the fourth. Right, you can see all these things coming together. This is going to be t to the fourth plus 2t to the fourth, 3t to the fourth. This is going to be 1, 2, 3, 1, 3, 4 t to the fourth, and I'd get 3/4. And again, because 3/4 and 1 are not equal, my limit does not exist. Thank you for visiting my limit existing 3D fun TED Talk. Parametrics for 3D. Paths for 2D. You're trying to make the degrees match so my fractions reduce and I get nice numbers.